Alright guys, so I'm here for this next video. We're going to talk about this question basically. What do the first and second derivatives tell us about the graph of our original function? Okay, so normally this is something that I would just go ahead and give to you guys in class to fill out. So I'm going to put a PDF on the website if you want to fill it out that way, or you can just write this down your own. Okay, so let's talk about the first derivative first. So if f prime is positive on an interval, that means that our graph is increasing as we go to the right. If we have a positive slope, that means our function is going up. If my first derivative is negative, we have a negative slope. So it means the graph is decreasing as we go to the right. It's going down. So for example, if I just give you say a graph that looks like this, right? What we would do is we have to say where is this graph increasing and where is it decreasing? So where is it decreasing? We see a negative slope up to this point here, which looks like roughly at -3. So I would say in this case, we are decreasing on the interval from -infinity to -3. And we're going to be, actually, I'm going to make this curve a little more exciting. So let's make this curve go there. And then we'll go up. And then we'll go down like that. Okay, so we're decreasing from -infinity to -3. And then we'll also see that we're decreasing from there, which looks like around 6, on to infinity. So, and 6 to positive infinity. As for where we're increasing in the middle where we see we're going up, right? So we're increasing as we go from -3 to 6. Now, you might notice I'm using solid brackets here. So when we're doing increasing and decreasing, we always like to use closed intervals like this, like 3 to 5. Or say -2 to infinity. Now you always use an open around infinity like that. But anytime you have a number with increasing or decreasing, we do a closed bracket. And that just means on the entire interval -3 to 6, we're increasing. We talk about over that interval. All right, now suppose I give you something like this. Just an equation. If I want to see where this is increasing or decreasing, what I'm going to do is I'm going to make a sine line graph of f prime. So, because the sine line graph tells us where something is positive or where it's negative. So I'm going to find the first derivative, so 2x minus 6. So if I set that equals 0, my only critical point is x equals 3. So if I make a sine line graph at 3, and then I plug into f prime, that's why we're always going to label it. If I plug in 10, I have 20, my 6 is positive, plug in 0, I get -6. So this function is increasing on the interval from -infinity to 3. And by increasing, of course, I mean decreasing. Because my first derivative is negative. And we are increasing, where my first derivative is positive, from 3 to infinity. And again, that's since my f double prime is a positive number, and it's decreasing there since my, f single prime, since my f single prime is negative. We want to always have kind of these justifications like that. It's increasing because my first derivative is negative. Decreasing because my first derivative is negative. Increasing because my first derivative is positive. Okay, so that's the first derivative. Now let's go ahead and talk about the second derivative. So the second derivative tells us about the first derivative, of course, right? Because we know that f double prime is f prime's derivative, also known as the slope of f prime. Okay, so just thinking back here, if my first derivative is positive, that means the graph of f is increasing. So if my second derivative is positive, that means the graph of f prime is increasing. F prime being the slope of f, it means the slope of f. So the slope of the graph f, that's f prime. So f prime is increasing. And the name for this is we call it concave up. So you could have a concave up function that's increasing, where again, that slope is getting bigger, it's getting steeper. You could have a concave up graph that is decreasing, so something like that. Or you could just have a function that's like a parabola is always concave up. And I think about this that it opens upwards. It's like you have a cereal bowl that opens upwards or part of that cereal bowl. Okay, now here's an interesting fact that you're going to see occasionally. One thing you'll notice is if you have a concave up graph, if you draw a tangent line, no matter where you draw it on a concave up curve, on any concave up curve, your tangent line will always be below the curve. No matter where you draw it, it's always going to be under the actual curve. It's an underestimate of the curve. Okay, so that was concave up. Now the next thing we're going to talk about, of course, is concave down. So concave down is what happens when my second derivative is negative. And that means that my first derivative is decreasing. So again, the first derivative being the slope of the graph, my f prime is decreasing. So my slope is getting smaller. So what that could look like is, in general, again, it could look like your bowl that got flipped upside down, a downwards parabola. You could have a concave down graph that was increasing. So for example, like a natural log graph is concave down. You could also have a concave down graph that's decreasing, like my portfolio when the lockdown started in March. Okay, and another thing you'll talk about here is doing the same logic when we have tangent lines on any concave down graph. Any tangent line on a concave down graph that you could draw is always going to be above the curve. And one tip here, when you have concavity, and this is going to be different increasing and decreasing, we always use open intervals to talk about concavity. So we say it's concave up on 3 to 5, or concave up from 7 to infinity, something like that. Okay. One more thing I want to talk about, this is a special term, and it's kind of analogous to a maximum or minimum, a point of inflection. So a point of inflection is where the second derivative changes sign. So where does your second derivative switch from positive to negative or vice versa? Okay, now anytime you have a point of inflection, it's kind of like a critical point. Your second derivative could be 0 or it could be undefined when you're switching from positive to negative. And again, do a sine line graph, right? A sine line graph is what shows you where does the sign change from positive to negative. What this looks like is, say you have a graph of f of x. If you have a point of inflection, it's like somewhere around there. It's hard to find the exact point without an equation, but the idea is that like you're concave down on the left side of it, but if you, let's switch colors here, but you're concave up on the right side. And again, it's hard to pinpoint the exact value, but the point of inflection would be somewhere around there. It might be easier to see if you had like a shark fin. So for example, if you had a graph that was concave up and then concave down, that would be your point of inflection right there, or your POI. Okay, so that's what's going on there. Let's talk about a problem here where I give you a function, I ask you to find the coordinates of the points of inflection and the intervals where f is concave up down. So point of inflection, concave up down, that's talking about the sign of f double prime. So I'm going to make a sine line graph. So I got to find f double prime first. So f prime here would be 4x cubed minus 36x plus 3. So my second derivative would be 12x squared minus 36. So if I set that equal to 0 to try and find any like inflection points, I can factor it out like that. So if I try and solve that, x squared minus 3 is 0, x squared equals 3, so your x is plus or minus square root of 3. So that's telling you, and this is why we label it, if you draw a sine line graph of f double prime, you split it up at rad 3 and you split it up at negative rad 3. So when you make your sine line graph here, again, it's a sine line graph of f double prime, so we need to plug in f double prime. So we're going to take values and plug it in probably to the factored form right there. Okay, so when I plug in 0, 12 times negative 3 is negative. If I plug in 10, I have 12 times 97, which is positive, and same thing on there. So to kind of answer this question, let's go ahead and figure this out then. Let's pick purple here. So we are concave up when your second derivative is positive. And that happens on the interval from negative infinity to negative square root 3, and also on the interval from square root of 3 to infinity. You are concave down, and by the way, this is how you should be writing it up on your homework and writing it up on the test. You're concave down when your second derivative is negative, and that happens on the interval from negative rad 3 to positive rad 3. A point of inflection happens when your f double prime changes sign. So we see that in 2 points here. We see that right here and right there. We see 2 times our sine line graph changes positive, negative, or negative to positive, and that happens at rad 3 and negative rad 3. Okay, so those are the points of inflection. That's concave up down. And one key point, at a point of inflection, it must change sign. This is key. I always see chumps that just think a point of inflection is when your second derivative is 0, but the sign change is crucial. And the examples I gave here are, look at x to the 4, right? Because if you take the first derivative, you get 4x cubed. The second derivative is 12x squared. If you make a sine line graph of f double prime, you split it up at 0, there's no sign change. And sure enough, this is not a point of inflection. If you were to graph this x to the 4, it's similar to a parabola in the sense that it's always concave up. So this is not a point of inflection because it doesn't change from positive to negative. Make sure you see that change of sign in the second derivative. Okay, so thanks for watching. Bring some questions. I'll see you in the next video.